Today we have Isaac, our own PhD student, the second year at CMU. He's going to talk to us about optimal scheduling on multi-server servers, and the floor is yours.
All right, thanks, Pedro. So my name's Isaac. I'm going to be talking about optimal scheduling for multi-server systems. This is work with Zeev Scully and Mor Harkel-Bolter, my advisor. And this is work that's going to appear in Performance 2018. Before I get into that, I want to talk to you about two different kinds of analysis. One kind is worst-case analysis. So in this setting, we think of having adversarial inputs. There's some big bad adversary, and they send us inputs, and it's going to be whatever's the worst for our algorithm. And the question we're always answering is, how does my algorithm perform on its worst-case inputs? Now, there's something really good about this kind of analysis. If we can prove something about the worst-case input, then that's true about every input. So it's a very general form of analysis. On the other hand, there's some problems it's not right for. For instance, on an online problem, it could be the case that every online algorithm has a competitive ratio that's poor or even unbounded in some cases. So for those problems, worst case analysis doesn't do what we want. On the other hand, there's stochastic analysis. So in this case, rather than having adversary, there's just coin flips. We have random inputs, and our question is, how does our algorithm perform on average? Now, the downside is all our results will just be about averages. They won't say things about all inputs. But on the plus side, there are algorithms that do quite well in practice, and they do well because they do well on inputs that look more random rather than ones that look adversarial. Moreover, often stochastic analysis can tell us these algorithms perform well on random inputs and these perform poorly, rather than a worst case analysis that might say everything has its terrible competitive ratio, let's just throw our hands up and go home. So what this talk is going to be about is stochastic analysis. Now let me introduce you to the setting. This is the MG1. It's a single server system, and basically jobs show up. The jobs are these blue rectangles, and they at some point, and we have a scheduling policy that says these jobs receive service at this time. Each job has a size that's the height of these blue rectangles, and that just says what the service requirement of the job is, how long it needs to be at the server until it's done. Now, because this is a stochastic problem, we're not going to have worst case job sizes. Instead, job sizes will be sampled IID from some job size distribution, which we'll represent with this S. Likewise, arrivals won't be at worst case times. Arrivals will come according to a Poisson process with average rate lambda. Now, so as these jobs go through the system, they eventually reach service. And as they receive service, they might be somewhat completed and more over time. We call this the amount of work that's been done on a job, its age, and what's left, its remaining size. Eventually, the job completes. And what really matters to a job is its time from when it arrives in the system to when it completes. We call that amount of time its response time, which we represent with a T. And this will be our important metric. We're going to try to choose a scheduling policy to minimize the mean response time over all jobs. Now, we're going to assume that jobs are coming in slow enough that we can keep up with them. The server can get everything done. And that means every now and again, the system will be empty. The server will have completed everything. We'll call the fraction of time that the server is busy rho. We'll also call this the load. Now, in order to get a better idea of what this is, let's imagine a timeline. At some times, the system will be empty, and at other times, it'll be busy, like this. Now, these intervals of time when the system is busy, we'll call those a busy period. And busy periods, we'll represent them with a B. These are things that queuing theorists understand very well. We know the mean length of a busy period. We know the distribution of the lengths of a busy period. We even know the length of a busy period started by a job of size X. So we understand everything about them. And they're going to show up throughout the talk. All right, so that's busy periods. Now, let's get back to our important question. We want to choose a scheduling policy to minimize mean response time over all jobs. So here's a question. What policy do you guys think might minimize mean response time over all jobs? That's E of T. Charlie.
Shortest remaining processing time.
Right. This is the policy that takes, at any time, the job with the least remaining size, so that's the one that's closest to done, and runs that job. We want to get the small jobs out of the way so that they don't get in the way of bigger jobs. And this policy actually has been known to be optimal for 50 years. Moreover, I've been talking about the stochastic MG1 setting, but actually this policy is even optimal in the worst case, in a worst case single server model as well. So it's optimal in both cases. But returning to our stochastic setting, there's another question we can ask, which is, what is the mean response time over all jobs of, or can we analyze the mean response time over all jobs of this SRPT policy? What do people think? Is that possible, or is it just going to be like completely intractable, something like that? What do people think? Take a guess.
Yeah, it's possible.
Yeah. So it turns out, yes, it is possible. Actually, this has been known for 52 years, since slightly before they proved it was optimal. So basically what I'm getting at is this single server system is understood really well. We know its optimal policy. We know the mean response time over all jobs of that optimal policy. We know it super well. That being said, there's something that's not the greatest about this setting. It only has one server. And real systems often have many servers. So it would be nice if we could take that into account when, and have a setting that incorporated that. So we're going to switch to a different setting, the MGK. This is just the same as the one server setting, except now we have k identical servers. So here's another question. What policy might be a reasonable or maybe even optimal policy for this setting? I'll give you a hint. What was just the optimal policy that maybe we can transfer here? Yeah? Exactly. So we're going to call this policy SRPT-K. Run all k jobs with least remaining size.
So it's one thing, you don't charge yourself for kicking the job off a machine and starting a new one then?
Right. We call that preemption, and we're going to assume that preemption is free and we retain all the work that we've done so far. We could definitely try other assumptions, but this is the one we'll be doing for this talk. All right. So with this policy, oh, yeah.
So are the job sizes the same for all machines? Or?
So we're going to assume all the servers are identical. So a job just has an inherent service requirement. It doesn't matter what machines it runs on. Good question. All right. With this policy, SRPT-K, there's a natural question to ask. Does this policy minimize mean response time in a k-server system? What do people think about this one? Yeah. You don't think so? No. All right. Well, you're right. So there's two ways to answer this question, and one of them you're definitely right. So one way to answer this question is in the worst case setting, the adversary again. In this setting, the answer is definitely no. SRPT-K is not optimal. In particular, there's a paper by Leonardi and Ross from 1997, and it shows that the competitive ratio between SRPT-K and an optimal offline algorithm can be as much as the logarithm between the biggest and smallest jobs. Now, if you think about that in the setting of a real system, you could have one job that takes on the order of nanoseconds to complete, and another job that takes days. Those are both pretty realistic to show up in the same system. And because this is actually a log-based 2, once you pull all the constants out, that's actually 50 factors of 2 apart. So we could have a competitive ratio as bad as 50. That's the sort of thing we really need to worry about. So from the worst case side, it doesn't have a good competitive ratio. But we can also ask the same question in the stochastic case. The stochastic case is an optimal policy. And this is an open question. That's what the rest of the talk is going to be about, trying to analyze SRPT-K in the MGK setting. All right. So now let me show you our results. The first result is that we give the first analysis of SRPT-K for the MGK system. And this is a pretty big deal. the MGK system, all people have really tried to do in the past was analyze these simpler policies, like first come, first serve. And even on those simpler policies, the only results they could get were these approximation results, and people have even proven those approximations could be arbitrarily bad in some cases. So people really didn't know much about the MGK. So that's why this is a big deal. Now we get a bound on mean response time. It's not an exact analysis. That being said, the bound is tight in the limit as load goes to 1. That's the limit as all the servers are busy all the time. And moreover, we use that analysis to prove that SRPTK has optimal mean response time over all jobs in the limit as all the servers are busy all the time. So in that sense, it is optimal. And the reason we care about the limit as load goes to 1, as all the servers are busy, is because if load is very small, then basically all the jobs get their own servers, and the scheduling policy doesn't matter in the slightest. So there's not really much point looking at it in that case. Instead, we look at the case where the servers are busy, and so scheduling really matters. Also, as a bonus, this analysis generalizes to give the first analysis of several other scheduling policies, although I'm not going to talk about that today. Yeah?
Will at some point you have a formal definition of optimum? Is that coming up at some point?
Yeah, that'll be on the next slide. Okay. So, all right, so let's go into a little more detail about what our, about how this result is going to look. As I said before, we understand the MG1 system very well. We'd like to understand the MGK system better. So we'd like to have, so what we'll do is we'll imagine that the K servers in the MGK system, they'll run at speed 1 over K. And the one server in this system runs at speed 1. So both systems will have the same overall speed. And with that in mind, we can actually simulate any sort of work going on over here using this system, because it runs at the same speed and it's just got one server. And what that means is that the mean response time in an MGK for the optimal policy, whatever that policy happens to be, maybe it knew the future, whatever, has to be at least as much as the optimum under an MG1. Now, clearly, the mean response time under SRPTK has to be at least as much as the mean response time for the optimal policy. But, and on the other hand, we know what the optimal policy for the MG1 is. We know what minimizes mean response time. It's just the SRPT policy. So from looking at this equation, we see that mean response time under SRPTK is at least as much as under SRPT. Now that's probably not surprising. But here's the part that is surprising. What we're going to show is that the mean response time under SRPTK divided by the mean response time under SRPT converges to 1 in the limit as load goes to 1. So this is a pretty big deal. Like, this is optimal even on this better system, and we're going to converge to it. And the thing to notice is the optimum policy is sandwiched in between SRPTK and SRPT. So proving this ratio will also prove that the ratio between SRPTK and whatever that optimal policy is for the MGK also converges to 1 in the limit as load goes to 1. That's the sense in which we mean it has optimal mean response time for all jobs. SRPTK is optimal as load goes to 1. That's in the limit as all the servers are busy all the time. Yeah?
If all the jobs are preemptible, what's preventing you from simulating MGK SRPT? What's preventing you from simulating MG1 SRPT and MGK SRPT? Why can't you go one way but not the other?
Sure. Imagine we only had one job, okay? We start running at one server. We can preempt it and then run it at another server, but we're still never running it at more than one server at a time. And so it'll take K times longer than it would under SRPT1. Yeah?
Drawing on my minuscule knowledge of queuing theory, both these top and bottom are infinite, right? So like...
which ones are infinite?
I mean, as
here
the
and
load
here?
goes to 1, the response time goes to infinity.
So that's why we're taking a limit. We're not actually going to evaluate it at load equals 1. We're just going to get closer and closer.
Yeah, but your argument is it says something useful about when you care about it, like when the as you get very close to 1, the response times are almost all infinite. So maybe that's not a situation you really care about.
So you might care more or less about that. But we actually prove more than just what happens right at load equals 1. We also prove things about how it converges there. And so we can say things where the load is high but not yet infinite, the ratio is already very close to 1. And I'll show some graphs later in the talk about this. OK, so this is how we're going to try and prove things about SRPTK. So now let me give you an overview of what the rest of the talk is going to look like. First, we're going to analyze the mean response time over all jobs of SRPTK in the MGK. Next, we're going to show that SRPTK is asymptotically optimal for the MGK. And finally, I'll give some empirical evaluation so you see exactly how that plays out in the real world. All right. So in order to get started, we're going to go through an example. But in order to do that, we're going to need some definitions. Now, we're not going to try to analyze all the jobs at once. Without loss of generality, we can focus on a single job. We'll tag one job and focus on just that one. So we'll focus on this job J. Let's call its original size X, and what we're going to try to do is bound the response time of this job J. Now, because it was just an arbitrary job, bounding this will allow us to bound the overall mean response time. Now, there's a very useful property about SRPTK that we're going to use here. Whenever J is in the system, either there's a server working on J, or all the servers are working on jobs with less remaining size than J's remaining size. We'll call those jobs, the ones that can get in front of J, the relevant jobs. And we're going to use those in our analysis. All right, so now let's run through an example, now that we know what the setting looks like. So let's say we have these 3 servers, K will be 3. We're going to organize the jobs in terms of remaining size like this. So the smallest one will go here, middle, biggest. And let's say at the moment J shows up in the system, we have these 5 jobs, A, B, C, and Z. A, B, C have smaller remaining size, Z is larger. So now here's a question. What jobs are in the system right when J shows up? What jobs are in service right when J shows up in the system? ABC, yeah. Perfect. So these are the ones running. They're running. Let's say nothing arrives. What's going to happen next? Just shout it out. All right. So I heard 2 things, and they're both right. A finishes service, and J joins the queue. So that's what happens right when A finishes. B slides up, C slides up, and J joins the system. And we can continue like this. So the next thing that will happen is B will complete, and C will move up. And that could happen for a while. But let's assume after only a little bit of time where C gets to be the smallest, something different happens. There's a new arrival. Let's call it job N. So N will slide everything up, and it'll force Z back out of service, and we'll have N, C, and J in service. Then if there's no more arrivals, N will complete, so C will be first, then C finally will complete, and finally J will complete. So this is J's entire time in the system. Now, the thing this analysis is going to focus on is the amount of work done while J is in the system. Let's draw this box. Everything in here is work done while J is in the system, or servers are idle. Now, this work is interesting, but the key thing we want to bound is the response time of the job J. So where in this picture does the response time of the job J show up? Anybody tell me? Yeah, it's the length of this rectangle. So the length of the rectangle, that's just the area of the rectangle, the amount of work done while J is in the system, divided by the height of the rectangle, which is the rate at which work is being done. So we can bound T of J if we can bound those 2 quantities. But actually, we know the height of the rectangle. We know the rate at which work is being done. Remember, all the servers run at speed 1 over k. In this case, 1 over 3. That means the height of the rectangle, the speed work's being done, is just 1. So we actually know the height, So all we have to do is bound the area, that is the work being done while j is in the system, and we'll be able to bound the response time of j, which is the thing we care about. All right, in order to bound this, we're going to split the work into various categories. In order to do that, let's think about the different types of jobs we have. So there's the tag job, j. There's relevant jobs, which are the ones with smaller remaining size than j's remaining size, and irrelevant jobs, the ones with larger remaining size. We can actually break this up a little more. We can think of old relevant jobs, the ones that were in the system when j showed up, and new relevant jobs, the ones that arrived later. With those 4 categories, we'll define 4 categories of work: virtual work, tagged work, old relevant work, and new relevant work. Now, in the virtual work category, we'll put all the work done on irrelevant jobs, and we'll also throw in these periods when servers were idle. So all of that gets lumped together into virtual work. With these 4 categories, all the work that happens while j is in the system is in one of the 4 categories. Meaning that if we can bound all 4 categories, we'll be able to bound the amount of work done while j is in the system. Yeah?
And our ordering scheme guarantees that the job never changes categories, right?
Right. The reason a job can never change categories is because basically the remaining sizes of 2 jobs can't interchange. Because if a larger job is getting service, the smaller job is as well. And so they both move down in remaining size in lockstep. So things are only in one category throughout their time in the system. All right, so the easiest of these categories to bound is tagged work. That's just work on the tagged job j. We know how much there is of that. There's x tagged work. Next, we can bound the amount of virtual work. Now, virtual work can only happen while the tagged job is in the system, because it has larger remaining size than the tagged job. And there are only k-1 other servers for virtual work to happen at. That means that the amount of virtual work done while j is in the system can be at most k-1 times x. So we've got those 2 bounded. Now for new relevant work, these are just sort of the extra work caused by arrivals in the system. This is just like in a busy period from earlier, the extra work in a busy period caused by arrivals. And we can analyze it with the same techniques. This means the only difference is, rather than all arrivals being counted, like in a busy period, only relevant arrivals will be counted. So it's just a shorter busy period. So we can use a relevant busy period to analyze this. This is also something CMU theorists already understand well. The final category is old relevant work. And that's a little more complicated to bound. We're going to do that next. So we've got 3 categories bounded, and if we can bound the 4th one, we'll have everything we need. All right. So now, let's think about the amount of relevant work in the system over time. Because when j shows up, it'll see how much relevant work there was when it arrived. So in this case, relevant work, the definition here, is the amount of work made up of jobs of remaining size at most x. This is because these are the jobs that will be relevant if j were to show up at this time. So we can graph that over time. We have a problem. This SRPT case system, this MGK system, as I said earlier, it's really not something that queuing theorists understand very well. Unlike all those other things I talked about, this is a bit of a blank spot. But we can relate it to another system that we do understand well. We can relate it to an MG1 system running SRPT. In particular, we'll imagine we have these 2 systems, and we're running them both at the same time, receiving the same arrivals. And what we're going to do is show that the difference in relevant work between the 2 systems, if they receive the same arrivals, will always be small. We'll call this amount delta t. And in particular, we're going to show that delta t is never greater than kx. So what that means is that SRPT k's relevant work always stays in this river between the relevant work in SRPT1 and kx more than that. And remember, we understand the MG1 system. We understand SRPT in the MG1 system. So this bound will give us a bound relative to something we understand and therefore can use. Yeah?
So this is for total relevant work or just the old relevant work?
So this is So at this point, it's just relevant work. Remember, J hasn't arrived yet, so there's no old or new yet. This is the stuff that will be old relevant work once J shows up.
Okay.
All right. So our goal is to show that delta t is never more than kx. So the way we're going to do this is by dividing time into two periods. We're going to have few jobs intervals where there are less than k relevant jobs in the SRPT-K system. This means at least one server in the SRPT-K system is either idle or doing irrelevant work or something. In the many jobs interval, which will be all the other time, there are at least k relevant jobs in the SRPT-K system. So all the servers will be doing relevant work. And we'll prove this property about delta t in both cases. First, let's start with few jobs intervals. In this case, at most, there are less than k relevant jobs in SRPT-K. But a relevant job can have at most remaining size x. So it contributes at most x relevant work. That means the total relevant work in the SRPT-K system is at most kx. So this is great. Few jobs intervals, if there's only kx relevant work under SRPT-K, then the difference between that and SRPT, this difference here, is certainly no more than kx. So in that case, we've got it covered. Delta t is no more than kx. In the many jobs intervals, there's at least k relevant jobs in SRPT-K. In this situation, the servers, all k servers, are running relevant jobs. This means we're completing relevant work at speed 1. There's no way the SRPT1 system can complete relevant work faster than that. Which means, since SRPT-K is completing relevant work at speed 1, it's completing it at least as fast as the SRPT1 system. And consequently, delta t is decreasing. The only other thing that can affect relevant work is arrivals. And the same arrivals show up at both systems. So that doesn't affect delta t at all. So delta t is decreasing throughout these many jobs intervals. And we know it starts the interval no more than kx, because it starts the interval from a few jobs intervals. And then it decreases throughout, or at least does not increase. So that means delta t is at most kx during a many jobs interval. So putting these together, we have what we wanted. At all times, delta t is at most kx. And that means we can bound the relevant work under SRPT-K system in terms of things we understand. The relevant work under SRPT-K is no more than the relevant work under SRPT1, which we can explicitly calculate, plus kx. All right, we've got everything. We had 3 categories before, and we've added our 4th category. Now we can bound all 4 categories, and consequently, we can bound the amount of work done while J is in the system, and therefore the response time of the job J. So these 3 categories, these are basically the work that we can see coming right when we arrive. Old jobs, ourself, and this sort of wasted virtual work. Then on top of that, there's these relevant jobs, the ones that come up later. The way queuing theorists represent these relevant jobs is with this symbol, this busy period sub less than or equal to x, meaning the relevant busy period. And then the amount is, at most, x from the tagged work, k minus 1x virtual, and this amount that we just found of old relevant work. And we can bound response time like this. So this is the response time bound. Okay, so now let's take stock of where we are. We've analyzed mean response time of SRPT-K in the MGK. In particular, we've bounded it. Next, we want to show that SRPT-K is asymptotically optimal for the MGK. And we're going to use this bound to do this. So here's how we're going to do that. Here's what our result was. The response time of a job of size x is at most these 4 categories. So now we'll do some algebra, and what we can do with this bound is show that the mean response time over all jobs, not just the ones of size x, under SRPT-K is in most of the mean response time under SRPT1 plus this extra C log 1 over, some constant times the log of 1 over 1 minus rho, the load. All right, so this is our bound. What can we do with this bound? Well, there's a very powerful result thanks to Lin, Weirman, and Zwart. What they showed, this result, this holds for all rho, no matter what. This is just a bound. It's great. But we can take this extra result by Lin, Weirman, and Zwart. What they show is that the mean response time under SRPT1 in the limit as load goes to 1 is asymptotically larger than log of 1 over 1 minus rho, subject to some technical assumptions about the job size distribution. So this is asymptotically larger than this. As a consequence, in the limit as load goes to 1, this term dominates. And what that means is that the mean response time under SRPTK over the mean response time under SRPT1 in the limit as load goes to 1 converges to 1. That's what we wanted to show. And now we've shown it. All right. So now let me show you what it looks like that this ratio is converging to 1. So I'll show you what this ratio, mean response time for all jobs under SRPTK over SRPT1, for a specific system with k servers. So this is a system with uniform job size distribution between 0 and 1. This is the ratio, and this is the system load. And so we show the bound we give via analysis, and also the simulated results of this system. And likewise, we can do this for a job size distribution with a bit more variance, when it's hyper-exponential with higher coefficient of variance. Now here's what I want to point out. Look at this region. This is where load is getting high, and both the simulation and our analysis, in both cases, are converging to 1. So what we said is really true. This ratio does converge to 1 in the limit as load gets large. All right. So just to recap, we've given the first analysis of SRPTK in the MGK, in particular bound on mean response time. We used this, and we showed this bound is tight as load goes to 1. And we use this bound to show that SRPTK is optimal in the limit, it has optimal mean response time over all jobs in the limit as load goes to 1. We did it with an example like this. So thank you. Yeah, any questions? Yeah.
Can you use the distribution assumption for this analysis? Is it in the optimality of SRPT1?
Which distribution assumption are you thinking of?
Didn't we assume this, could we assume, like this wasn't a worst case scenario?
Yeah, the job size come from some S? Yeah, so if we go back to here, this busy period thing, well, this busy period thing really only makes sense if we have a job size distribution, and we only know how to analyze relevant work under SRPT1 if we have a stochastic assumption like this. So that's where we used it. Yeah.
Just sort of push back the same point as before. Like,
Uh-huh.
I mean, you said when the load is light, you don't care about the scheduling algorithm because they're all fine.
Yeah.
Also, I would say when the load is 1 minus 10 to the 4th, and the minus 4th, you also don't care because every scheduling algorithm is going to suck if they're that highly loaded.
Sure.
So,
but
like, what does the result say if the loads? I mean, what you care about is the range where some algorithms suck and some don't.
so here's a scenario where this is highly relevant, okay? What if your system is usually fine? Okay, usually load's pretty small and you don't care. But every now and again you get these spikes of big load. Maybe even it spikes so much the server can't keep up. Our results also show that even when you have these giant spikes, you do pretty close to optimal in dealing with those giant spikes of jobs. And that sort of temporarily increased traffic is something that definitely does come up in real systems.
Yeah, but everything, I mean, if it's overloaded, then everything does fine, because you're just getting rid of work at the rate that...
So actually, surprisingly, that's not the case. For instance, if you do a first come, first serve sort of system, everybody's just sitting in this massive line. Whereas with a policy like this, at least the small jobs are still getting done reasonably well.
So like, what does this say if the load 75%? I mean, that seems like the reasonable range.
Sure.
On that.
So This does give a bound on the performance under this reasonable range. Unfortunately, it's not a very tight bound at that. And this is definitely something I'm interested in going forward, but these techniques aren't the right ones to analyze that. Yeah,
So
Ben.
is there a result known like this for any other algorithm in this environment?
Well, the same mechanisms that allow us to prove these things about SRPT, we can also do for policies like preemptive shortest job first, where we just focus on the original size, not the remaining size, or FB, which is where we focus on the age, not the size.
So for shortest job first, it also converges to one like this? Is that?
Yes. Yeah.
You had a busy period formula. Why is it based on the z job as well?
You mean this? Sure. So here's a scenario that could happen. Maybe, you know, there's lots of work in this. There's the work. The job is running for a bit. We're doing some virtual work, as in working on these irrelevant jobs, and then a flood of arrivals show up after we've worked on some irrelevant jobs for a while. So that irrelevant work, that's work that sort of we can foresee it could happen. We can't necessarily avoid it.
Thank you.
Sure.
So could you replace time to finish by expected time to finish?
Yeah, so that's what we get here. This bound.
No, we know
Oh.
the job. So you say you know how long a job's going to take.
Oh,
so
yes.
It's been in the queue for 10 seconds, and then there'll be an expectation of how long
Right.
it's going to take to finish.
Right. In this talk, I assumed you knew exactly how long every job was going to take, but maybe in the real world you have a distribution. So people do run the expected time to finish, or there's another policy called the Gittins index policy for these sort of scenarios. I don't have results about those policies yet, but I think it's possible that a similar sort of approach could work. All right. Thank you.